Hi, everyone. Nice to see so many familiar faces. And please interrupt if you have questions. So I want to start off by talking about, was there a question already? Yeah. Yeah. How many familiar faces? Okay, so I want to start off by talking about bases in cohomology. So, let's say you have X smooth compact manifold, and H of X is the cohomology, let's say, over Q. Then how do we find a basis for the cohomology? So one standard way is to try Morse theory. So if I choose a Morse function, then there's a Morse complex generated by the critical points of F. And this has a boundary operator which counts the isolated gradient trajectories. And computes the cohomology. So in good cases, you get a basis this way. For example, let's take something like the blow-up squared of S2 times S2. So this is a toric variety, and it maps to say this hexagon under the moment map. And one of the natural ways of getting a Morse function is to take the pairing of, say, the moment map with so some generic component of the moment map will give you a Morse function in this case. So let's just see whether people are awake. The dimension of the cohomology is 6 because that's the critical points are the fixed points of the torus action. So so they're 1, 2, 3, 4, 5, 6, and well, this boundary operator is counting isolated gradient trajectories, and because there's a torus action, there isn't any gradient trajectory that's isolated. So the boundary operator is just 0. So in this case, the Morse complex is exactly the cohomology. And so you get a basis even if you look at this a little bit more closely. So the way you would get the basis is you would just take the closures of the unstable manifolds for the Morse function here. So for this one, the unstable manifold would just be a point. And then you would get, so this would be my first cycle, my second cycle, my third cycle. And then here's another one. Here's another one. And then the unstable manifold, for this guy would be the whole thing. So that would be your, C5 would be your top dimensional cycle, and that would be your basis for the cohomology in this case. Okay, so that's that's one way of doing it. But there's another strategy. Which is to use the minimal model program. And the rough idea in sort of a symplectic version is that you start varying. Let's say x omega is symplectic at least. And you try varying omega in the direction of minus C1 of x. And then whenever omega becomes degenerate, then you do some sort of surgery. And the surgeries in the MMP, they're called either, for today I'll just pretend that they're either blowdowns or flips. And so what these are, if you start off with x, then inside x you find the locus where it's non-degenerate, and this turns out to be the projective bundle, if you're lucky, over some other submanifold. And this other submanifold is called the center. So if you're just doing a blowdown of some divisor to a point, the center would just be a point. But you can have blowups along higher dimension varieties as well, and so then that would be the center of the blowup. And so then, if you do a blowdown, you just replace this projective bundle with the center. But for a flip, then you have another projective bundle of complementary dimension, and replacing this projective bundle with this projective bundle gives you something called x prime, which is the flipped variety. Okay, so there's a whole theory of when you can do this. There's a giant theory in algebraic geometry, and then also there's a suggestion of Tian and Song and others that this should be equivalent in geometry. To Kähler-Ricci flow with surgery. But in both cases, in both algebraic geometry and in differential geometry, the theory is incomplete. But it's known in a lot of cases. Okay, so let me just give an example of how this works for the if I take the blow up squared of S2 times S2, then so my picture for the moment polytope was this rectangle with two corners cut off. And what's the first string class for x? It's the sum of the divisor classes I equals 1 to 6 di, where di is mu inverse of the ith facet. So these are the invariant prime divisors, and the sum of those is a representative of the Chern class for x. And so what's going to happen as I start varying the symplectic form in the direction of these sum of the di's is that these moment polytope is going to get smaller, sort of like this. And then eventually, as you keep doing this, the size of this, the area of this divisor is going to become 0. So that means that it's degenerate along that. And when that happens, then you do a blowdown or a flip. In this case, it's a blowdown. So this divisor becomes 0 area. You just blow it down, and then you sort of this one then becomes 0 after that. and then you go down to a point after this. Okay, so the minimal model program in this case would be x goes to a single blow up, and then just S2 times S2 itself, and well, then this it ends there. Okay, and it's an observation of Li Lin and Wang, and probably it's older than this, that in good cases, at least when z is a point, then the cohomology of x is just the cohomology of, which way do I want to do it? The other way. The cohomology of x is the cohomology of x prime, just some exceptional summand generated by, in the case of a blow up on a surface, it would just be the exceptional class, the class of the exceptional divisor. Okay, so here we got 6 cycles this way. In this case, you also get 6 cycles, but you get a different 6 cycles. So for the cohomology of S2 times S2, you could say take B0, B1, B2, and then B3. And then each time you blow up, you add the divisor class. So here I would blow up, which was my first blow up. To look and see which one was smaller. So my first, the second blowdown is the bigger one. So, so yeah, it's this one, and then, so then here, use a different color. So here you would get the basis of cycles. You would get the ones coming from S2 times S2. Forgot to do this one. B2, B3 is the whole thing. But then B4 would be this one, and B5 would be this one. So in this case, the 2 exceptional divisors are part of your cycle basis. In the Morse case, they wouldn't be. So it's just a different way of getting a basis for the cohomology. Okay. So what I want to talk about is a way of trying to do the same thing for the Fukaya category. But maybe before I do that, I just want to emphasize that this is maybe not as scary as it sounds. So let's do one more example. So suppose X is something like the product of 5 spheres, and I take the quotient by the diagonal action of SO3. And I ask, what's the dimension of the cohomology? So here I mean the symplectic quotient. By the diagonal. SO3 action. Does anyone know the answer to this? It's not quite as easy as the toric case, right? Because there's no obvious Morse function to take. Yeah, it's P2 blown up at 4 points because, how do you see that? You looked at it a million times. I think it's 4. We can because yeah, it's 4. Yeah. Yeah. So how do you how would you what would be your favorite method to try and do this?
Well, this was my thesis problem, so
yeah.
so space, but
Yeah. Okay. So I want to sort of look at this from the another I want to look at this from the viewpoint of the MMP. Yeah. Okay. Good. Yeah. So so being Fano is a property which is preserved by symplectic or GIT quotient. So this is certainly Fano here, and so when you take the GIT quotient, it's also Fano. So what one thing you can try and do here is you can try and look for an MMP running. I want to use this example to sort of show that it's actually not that scary to find these. So any guesses about what the MMP program was? I guess I didn't say what the symplectic form was. So the symplectic form is going to be some sum of standard symplectic forms on the different factors. And well, since this is a quotient, first you can look upstairs. So let's just look at S2 product itself 5 times. What's an MMP for this? Well, the first term class of S2 is twice the generator, right? So if I'm looking for a variation of symplectic form, which starts with this one, and which subtracts off, some multiple of the first term class, then it's going to be 2t1 up to 2t omega 5, right? And it's a basic fact that okay. So what's going to happen in the MMP for this is that eventually some of the areas of the spheres are going to become 0. Now that's not one of the MMP surgeries that I talked about. Instead, what happens then is you get what's called a Mori fibration. So you fiber over something lower dimensional, and that's considered to be the minimal model program. Okay, so the MMP for this one is pretty boring, but it's a basic fact that if you have an equivariant running upstairs, then you take the quotient, you get a running downstairs. So what happens here is that a running, the symplectic quotient of this pair by SO3 gives an MMP running for my original space. Now, for the diagonal symplectic form, if all of the lambda i's are equal, this is not that interesting, because then all the spheres are just shrinking at the same rate. So there are no surgeries in that case. But if I take the lambda i's generic, this doesn't change the topology, right? If I perturb the lambda i's a little bit, then I get interesting MMP runnings. And the surgeries in this MMP, they correspond to t's for which this quotient is singular. And when do you get a singular quotient? Well, you get a singular quotient when there's a point in here which is in the 0 level of the set of the moment mapping, which has a positive dimensional stabilizer. Well, if you have a positive dimensional stabilizer by SO3, it has to contain an SO2. And configurations which are fixed by SO2 just means that they're all on the same line. Okay, so for example, I could do something like this. Say I originally start out by looking at the space of pentagons with side lengths 1.2, 1. I have to make these a little bit generic so that I get some interesting MMP. and I start changing these lengths by the same rate. So one thing I can do is I can say I eventually get a surgery when my lengths are 0.5, 0.5, 0.7, 0.8, 0.9. Now, why is this a singular quotient? It's a singular quotient because there's a linear configuration in here. So I can have, say, the 0.9 and 0.8 vectors going this way, and then I can have the 3 other vectors, 0.5, 0.5, and 0.7, going the other way. This will be a point in this symplectic quotient, which is fixed by some SO2. And so then you can just look at what the surgeries that you get from those singular transitions are. So it turns out you get 3 surgeries, 3 blowdowns, eventually bring you down to an S2 times S2. And then you know that it's the del Pezzo given by blowing up P2 at 4 points. Okay, so, and there are different ways of doing this. Like if I would perturb the lengths in a different way, then I would get a different set of surgeries. I would then get a different MMP presentation of the variety and a different cycle basis for the cohomology.
Is this picture, am I right when you say this picture is like, I think this is like SAM05 bar, right? This space X.
Yes.
So is
Yeah.
the pentagon like the Mumford boundary, and then I have the areas of those spheres?
It's the moment map. This is this interpretation of the moment map, isn't it? You just think of these
I was wondering what this picture is.
Oh, what the picture means? Okay. Well, remember, my variety is a symplectic quotient of 5 S2s by SO3.
Yeah.
So each element of S2 I can think of as a unit, well, a vector of some length, right?
Yeah.
And then the moment map is the sum. Yeah, it's a picture in R3. Yeah. Thank you for that question. Yeah, so this is some moduli space of closed pentagons with some fixed lengths lambda I. And these are the configurations in that space which are actually lying in a line in R3. Yeah. Okay. Yeah. Okay. So let me now switch to Fukaya categories. So let's let now x omega as before compact symplectic, but also for so I can use the Chilibok-Munka perturbation scheme, assume it's rational, and L is a rational Lagrangian brane. And then, so associated to this, I have the Fukaya algebra. So I get the Fukaya algebra just by taking the Morse complex and tensoring with some Novikov. I'll take the universal Novikov field. And then this has operations, mu n, tensor n goes to CF of L, which count isolated configurations. You have some holomorphic disks. And then you have some gradient trajectories. And in the Chilibok-Munka scheme, what you do is you pick a Donaldson hypersurface. And this assumption that L is rational is an easy way of guaranteeing that you can choose this hypersurface so that any holomorphic disk is going to meet that Donaldson hypersurface. So, so you can mark the disks then with the intersection points, the interior markings are then required to go to the Donaldson hypersurface. And and then you use a domain-dependent almost complex structure to get transversality for these moduli spaces. Now, the moduli, these things, as they set them up, they don't have strict units, but there's a construction which is called homotopy units. Means that after you adjoin some additional elements to these algebras, they become strictly unital. So let's call 1 sub L the unit. And then you define a map from CF of L to itself by taking B to the sum of the mu n of B copies, n copies of B. Now, there's no guarantee that this sum is defined in general for any arbitrary infinity algebra, but you can check in this for Fukaya algebras that this infinite sum is well defined. And so you say L is weakly unabstracted. If the inverse image of the identity times the Novikov field is non-empty under this map. And then these are called solutions to the weak Maury-Cartan equation. So then once I fix some W, then I have a Fukaya category of objects are pairs with mu of B equals W, and the morphism spaces are CF L0, L1, A infinity bimodule. So the way you define this bimodule is if L0, L intersect 1 is clean, then you can pick a Morse function F01 on the intersection, and then you do a similar thing. It's the same sort of picture over here, but now where some of these gradient trajectories would be gradient trajectories on the intersection, and different parts of the boundary would have to map into the different Lagrangians. And then, in general, you have to worry about how to perturb them so that you get a clean intersection. Okay. Any questions? So the Fukaya category I just want to talk about is the disjoint union of the Fukaya categories for the different W's. So the rough theorem is that, so now the question is, how do you get generators? for the Fukaya category. And well, this is known in different cases. So, for example, for some Calabi-Yau varieties, it's known by work of Kontsevich and Seidel and Sheridan and other people. For toric varieties, it's known how to do this by Abouzaid and Fukaya, Ota Ono. Not much else is known. For curves, there's some other results, things like that, low dimension, but it's still about 100 years behind algebraic geometry, for example. So one common, and so what I want to talk about is a strategy for doing this, using the MMP. So suppose that x plus is obtained from x minus by a reverse flip or blow up. So in this case, we already know that this, at least if the center is a point, then it just creates a summand in the cohomology. We want to see if the same thing is true for the Fukaya categories. Now, a common objection is that for most x in algebraic geometry, you won't have a nice minimal model program. But I don't care, because even though the examples that algebraic geometers are looking at are way beyond what we can do in symplectic geometry at the moment. I mean, we don't even understand the Fukaya category of the Grassmannian or these Del Pezzo surfaces. So the objections about the MMP not working in general are so far removed from the class of examples that we're looking at in symplectic geometry that that's not really an objection for us. Another answer to that objection, so maybe I'm talking too fast. Am I talking too fast? The objection is that the MMP doesn't always exist, at least in the category of smooth varieties.
Or that if it exists, it isn't easy to read off the cohomology from it.
It isn't easy to read off the cohomology. Yeah, that's
singularities,
right. Yeah. Another aspect of the singularities is that if you allow orbifolds, the objections about singularities become much less serious. So, for example, for toric varieties, the MMP always works if you allow orbifolds. But from the algebraic geometer's viewpoint, they usually don't consider stacks in the MMP, and they just use the usual varieties. So things are actually much better than the algebraic geometers say, at least for many of the examples that we want to understand. Cannot be trusted. Yeah. Okay. Another thing is, because I'm working in symplectic geometry, I'm also allowed to deform the complex structure. And so that also allows me to avoid some singularities. It's still true that you can't always avoid them, but there are many examples in which this works. Yeah.
I just don't understand what a flip is.
Yeah.
In particular, I can't understand what's the difference between a flip and a reverse flip. I mean, they're not.
Yeah, good question. So, it has to be relatively phono. One of the morphisms, and the other morphism has to be the opposite. So, what you're doing in a flip is that there were these two projective bundles in the diagram, and
I mean, it's not, but it's not a birational. Or it is a birational.
Yeah, it's a birational transformation. Yeah, and the direction of the flip. This is a good question. There's not even a consistency in the terminology in the literature. But the flips that I'm talking about are always obtained by replacing projective bundles of some rank by projective bundles of lower rank. Like in the example of a blowdown, you would replace a projective space by a point.
Yeah.
And it's always something like that. Like of the projective bundle. That's right. Yeah, the reverse flip increases the rank. Yeah, and it also increases the dimension. No, that's the standard terminology. Yeah.
Is there a nice example of a flip that I could I'm not expecting you to do it right now, but just some simple flip that is not also a blow-up.
Yeah. So in the toric case, what you're doing, a flop would be something like this. So if a flop goes. You imagine that the polytope of the changes like this. So a flip, what it would do, it would change something like this. You have to imagine that I'm in one dimension more. So this is a 4-dimensional toric variety, and this is a P2. And you imagine first blowing up this so that I get a P1 bundle over this P2, and then I blow down in the P2 direction, and that just leaves me with a P1. So this would be an example. Yeah. Okay, so I want to suppose that x plus is obtained by x minus by a reverse flip or a blow up, and let's say it has point center. If it doesn't have point center, then you're going to have to worry about the Fukaya categories of these centers. And that's going to make the whole business much more complicated. So then what is it? Then you have some exceptional locus. Which is in E plus, sitting inside x plus, and this is just some projective space, Pn plus. So inside Pn plus, you just have the Clifford torus. So in my picture, this would be, something like here, something sitting in the middle of the projective space, away from the facets, and so then L plus is going to be a torus bundle over the Clifford in E plus. So if I would just look at this inverse, the inclusion of E plus in the whole space would just give me an isotropic. I have to thicken that up to get a Lagrangian. So that's going to be, L plus is going to be here, sitting a little bit away from the actual Clifford in the exceptional locus. Okay, so the rough theorem is that suppose that we're in the situation as above. Let M be the dimension of the added dimension that you get by going through this flip. So this is called the multiplicity. Then, first of all, there are M local systems on L plus giving weakly unobstructed giving weakly, is that better? Yeah, weakly unobstructed Floer non-trivial branes. L plus 1 up through L plus M in X plus. And let's see, I'll leave that up there. And and B, suppose that L1 minus up through Lk minus split generate the Fukaya category of X minus, then and L admit canonical variations into x plus. So what do I mean by canonical variation? Well, I'm changing the symplectic form as I go along. And there's no guarantee that I can move the Lagrangian along with this variation. Now, the variation that I'm doing is very special. It's in the canonical direction. And for Lagrangian, the restriction of the first Chern class to, oriented Lagrangian at least, the restriction of the first Chern class to the Lagrangian is trivial, right? Because the orientation gives you a trivialization of the canonical bundle. So at least cohomologically, there's no obstruction to carrying along the Lagrangians, but you still have to check that you can do that. Now, in the examples that I'm looking at, you sort of get this for free because you have lots of Lagrangians lying around. Like in these polygon spaces, you can just write down the canonical variations explicitly. But in general, you know, you might have problems with that. Okay, then L1 minus up through LK minus, and then I switched the subscript, sorry, plus 1 up through L plus M, split generate the Fukaya category of X plus. So, what are some examples? And this is just a really special case of the Abu Zaid et al. Result that, you know, for something like S2 times S2, if I start with the product of spheres, then I just have a single Lagrangian with 4 brane structures which generate the cohomology. It's just the product of equators. So when I blow up, there's no problem extending this Lagrangian to the blow up, right? Because it's just a torus fiber. So that's an example of where you don't need to worry about the existence of this canonical variation. So then this says that you just get an additional generator. Now the difference between the dimensions and the cohomology here is just 1. Right? I'm just adding 1 exceptional class. So there'll just be 1 brane structure on this exceptional Lagrangian. So here you'll get 5 generators. For the blow-up of S2 times S2. Okay, so a couple remarks. Proposed corollary of this is that if X admits an MMP, running with point centers, then then the Fukaya category of X is just the direct sum or the disjoint union of these different Lagrangians coming from the surgeries. So in particular, it should follow from this that if I take the Hochschild cohomology of this, and since I have these explicit generators, is semi-simple, and the Fukaya category is just splits as into sort of torus summons. So this means for such symplectic manifolds, the Fukaya category is really not that interesting. The interesting stuff happens when it doesn't split like this. But let's see. Where's my other remark? Okay, I guess that was my. Okay, so what's the any questions about the result? Yeah.
Can you say something about what happens to the W superpotentials?
Yeah, so the W will pick up some some corrections from the exceptional locus, but it won't change to leading order. That's basically what happens.
The fact that
Yeah.
that ring is semi-simple is a formal consequence of the fact that you split.
Yes, that's right. Yeah. Yeah. Okay, so there are two parts. So step one is that, and this is actually already quite hard, is really to show that these L plus 1 up through L plus M are weakly unobstructed. I mean, if I choose a random Lagrangian in a symplectic manifold, it's pretty hard to show that the space of weak Morey-Cartan solutions is not empty. So this is actually a lot of the work, and then the second part is the Abu-Zaid generation criterion, because I'm running out. Yeah.
Sorry, just to make
Yeah.
sure I understand the theorem, there's the implicit assumption that you make small blow-ups.
Oh yeah, that's a good question. So my blow-up, MMP blow-up, is not quite the same thing as a symplectic blow-up. So when I do a symplectic blow-up, I just cut off a corner, right? When I do an MMP blow-up, I'm flowing in the anti-canonical direction.
How long do you flow?
Yeah, as long as you want. Yeah, because what's going to happen is if I keep making these bigger and bigger, I mean, what Denis is sort of maybe has in the back of his mind is the fact that this is not the picture for an arbitrary size blow-up of P1 times P1. If I take a big blow-up of P1 times P1, then I'll have some other picture which sort of looks like I'll have three different Lagrangians with brain structures which I need to generate. But what happens with this one is that I cannot get from here to here by running the MMP. It has a different MMP which would blow down these exceptional divisors. Okay, so and so this Abu-Zaid generation criterion, let me just say a quick word about that. So I have the Hochschild homology of this of this collection of things coming from the minus part and things coming from the plus part. And then I have the open-closed map going to QH of x plus. But I already know that this splits as QH of x minus plus an exceptional part. So what you have to analyze here is the image of the two different sets of generators under the open-closed map. And this one is going to hit this part, and then this one is going to hit this part up to a small error term coming from the size of the blow-up. So because you can take the size of the blow-up arbitrarily small, you can see that it's surjective. And I should admit that there's some transversality issues here involved in extending the Abizay generation criterion to the situation that I'm looking at. And I haven't completely written those down yet. So maybe I'll find some further complication as I keep going. Okay, so what about this step one?
In that situation, QH of x minus is automatically subring QH of
No, it's just a subspace. Yeah, subspace. But actually, what this gives you is it tells you that, in fact, there's an adjustment of this classical splitting by a small error term, which actually makes it multiplicative in quantum cohomology. Yeah, that's a consequence of this. And Y.P. Lee and his collaborators have been working on proving that purely from the Gromov-Witten side. And I think they have, I haven't checked with him lately, but I think they have another proof that there is such a splitting multiplicatively. So, so in the last 5 minutes, I'll maybe just talk about step one. So step one is a bourgeois style SFT argument. So I have my X plus manifold, and I have my L plus Lagrangian in here. And I find a Z, which is a S1 fibered coisotropic. Over some Y. And so then I can collapse this coisotropic, and I get what's called a broken symplectic manifold. And so then there's a version of the Fukaya algebra for L inside this broken symplectic manifold. And so this counts what are called buildings. So these buildings are combinations of, disks in the left part, and then you can have spheres in Z times R, and then you can have spheres in X, the other part, and so on. I'm sure here everybody's seen pictures like that. The transversality is a little bit easier than the transversality in general because of the S1 fibration over the base. And these intermediate things will be gradient flow lines on this, on Y, this thing that the coisotropic fibers over. Okay, so then you get something which is homotopy equivalent. To my original Fukaya algebra. and this thing you can really compute, and you can really see that this guy is, 0 is even a solution to the weak Maury-Cartan equation in this algebra. And it's homotopy equivalent to this. And when you have a homotopy equivalence of A infinity algebras, you have a map of weak Maury-Cartan solutions. So the trivial solution in this A infinity algebra gives you some Maury-Cartan solution here. You don't know anything about it. It could be quite complicated. But all you have to know is that there exists one. And then from that, it's pretty easy to show that the Fleur cohomology is non-trivial just by looking at critical points of the potential. Okay, so I think I should stop there.